Okay, hello guys. So I'm trying to set up the two computers so you guys can see me better. Let's see. I don't want you to see me twice now. Okay. So I think that's good. Okay, so last video, but also last class, we talk about the least upper bound, but in particular the greatest lower bound, and let's see all this. We introduce the real numbers, right? So we introduce the real numbers. Also, before that, we did this proof that you are going to find useful today. Let me go back to this proof. This one over here. The absolute value of x less than a if and only if x between minus a and a. Okay. So we also prove this. Oh no, we didn't prove. We didn't prove the product. So I advise you to do it. This is in the book. And also triangle inequality. Today we're going to do triangle inequality. I think I cannot leave that. I want to do it. I want to do it. It could be an exercise, but we're going to use it so many times that I prefer to do it, discuss it in class. Okay. So as I said, we're following for analysis. We already started real analysis. We're following this book by Edward Gauden. Okay. So I like this book because look at its theme. It's very thin. Okay. As it should be, because this is kind of a review of analysis book. The book we have online, is too big. So I try to and it's available for us free, thanks to our library. And so I try to download it, and I try to print the first chapter. It's so big, it's no, I don't like it. So I like better this book. Okay, but if you want to have a better picture, more detailed picture of analysis and topology, you can follow the book. I will kind of try to rescue things from that book. Okay, so what we're gonna do. So we introduced real numbers last time, and the axioms, and we did the least upper bound and the greater lower bound. Okay, why is that important? Okay, so let me, because we did that, discuss that. Sorry, this is a calculus 3 class that I have to cover. So do look at that. I had to make a favor to a friend. I had to cover his calculus class. Okay, so let's start. So there is an exercise from the book that we're not gonna do. So I'm trying to use two computers so you don't look my nose. Okay. If I use my iPad, it'll be very hard to write. And last time my this part has been hurting for a whole year already, so I cannot really write on this. I have to put my hand on the top. Okay, so this is an exercise from the book that I advise you to solve. It's not, you don't have to do it for right now, but it'll be a nice presentation exercise. I will give you a chance to choose a problem to present, and this will be a good one because look at what it says. Let A equals the set of numbers so that R is a rational number and R squared is less than 2. Okay. So remember we showed that there is no solution for this equation r squared equals 2 in the rational numbers. So we show that if there is a solution for this has to be rational, okay? So you consider this set, is basically considering all the points that are less than 2, okay? And, such that the square of that number is less than 2. Basically, we know what we're trying to say is this. Avoiding to talk about the square root though. We're saying that we're considering A, all the rational numbers that are less than the square root of 2. So this is the set. Okay. But rational numbers are weird, okay? Because between any two irrational numbers, you can find a rational number. I think that's also an exercise somewhere, okay? So it's not like the rational numbers is a useless set. It's dense. It's dense in the real number. Between any two real numbers, you can find a rational number, okay? So why is interesting of this exercise is that you need to prove that A has no larger member. What does it mean? It means it doesn't have a maximum, okay? Because I'm considering all the rational numbers such that the square of that number is less than 2. Basically, all the rational numbers that are less than the square root of 2, but it doesn't have a maximum. So it means if between these 2 points, I always can find a rational number. Between these 2 points, I always can find a rational number, and so on. Okay? So that's why this upper bound greatest, I might not have to raise that class. This least upper bound is such an important property in the real numbers because later we're going to call it this kind of complete. So if you have a sequence of numbers, when we talk about limits, that's what we're going to talk about that today. What this set of numbers are going to, or this sequence of numbers are going to converge to a point of the real numbers. And that's not the case for rational numbers. So this is the example of, this is an example of a set where I can construct a sequence of rational numbers. I can construct a sequence of rational numbers that converges to a square root of 2. And a square root of 2 is not a rational number. So in that sense, the rational numbers are not close under convergence. Okay, that's going to be a very important property of the real numbers. Something that you don't learn in calculus, or in a regular calculus class list. So this is very important, okay? Because it makes the real numbers what make it so important. I already told you that the favorite or the most complete sets are the real numbers and the complex numbers. Okay. So this is an exercise that gives light of the definitions we were introducing last time, like the least upper bound and the greatest lower bound. And let me call it that sub and inf, okay? Because it's hard for me to remember those words. But sub, this is the sub. The sub of this set will be the square root of 2. And the inf, it doesn't have inf. Okay? Instead of saying lowest upper bound, That's the sub of A. Okay. Okay, that will be an exercise. That'll be a weird exercise. It's kind of a little bit hard, but it has a hint in the book. So you want to try it? Go ahead. Okay. Let me know how it goes. I don't want to assign very hard homework because I'm not very interested to scare anybody. But if it's in your interest, sure, go ahead, do it, and let me know if you have any questions. Now we're gonna do two more problems. I'm gonna type this on LaTeX, but I want to mention it. This because this exercise are gonna be fundamental later for proofs. Let's call it exercises or let's call it important exercises for later. Okay. So basically, in the homework, please make an effort, a real effort to try to prove all the problems. Okay. Something I want to do in practice with you guys is try to solve the problems live. Okay. So I'm gonna set this as the important exercises. For the theory. I'm gonna call it, let's call it proposition. It's a proposition. But this is in the book as exercise 43. It says, if x equal the sub of a set S, show that for each epsilon bigger than 0, there is A in the set S such that x minus epsilon is less than A and A is less or equal than X. Okay? It looks like it makes sense, right? And it's coming from the definitions, but please prove it. Okay? That's going to be homework. So what it's saying is you have a set S, right? So it could be any set S, and then you have the sub, right? It could be open, could be an open set, right? So, however, it doesn't have to belong to the set S. That's why we call it sub. Okay. So the sub of this problem, the sub of A, is the square root of 2, but it's not a rational number, so that's why it's not a maximum. Okay. So what it's saying is, if this is your X and you take epsilon, hopefully, let's see. I want to make sure I didn't know too much down. Okay. Hopefully, I'm not hearing any echo, so hopefully it's good. So if I choose minus epsilon, so let's say this is x minus epsilon. So let's say this is x minus epsilon. So this distance is epsilon. So it's saying that you can find an A right here, A, such that A is between x minus epsilon and x. Okay? This is what it's saying. So for every epsilon, you find an element of the set that is in the middle. So you cannot even move an epsilon below the sub. Okay? And the other one is similar. Let's say proposition 1 or proposition 2. This exercise 44, sorry. Exercise 44. This is exercise 45. If y equals the inf of the set, remember sub we said is the saying that lower upper bound of S, no? And the inf is the greatest lower bound of S. Okay, so I like it better inf and sub. Why is the inf? Show that for each epsilon bigger than 0, there is A belongs to S such that y is less or equal than A and A is less than y plus epsilon. Same thing here, no? So this is the real line, and S in this case is something like this, and then the inf is y, so this is y, and it's saying if you add epsilon to y, if you add epsilon to y, so here y plus epsilon, this is epsilon, you can find A. So you're gonna find this A here in the middle. So if the sub is really the sub, if you give something extra to the y, then you can find an element of S in the middle. Okay, that's what he's saying. Okay, so that's what I wanna say that, and we're gonna prove the triangle inequality, and I'm gonna give you two proofs. So I want to show you today. I want to show you that something you don't have live, right? Because we are not in the same classroom. But when I was a student, I remember these problems really scared me. I mean, really, really, I was just dragging to start this problem because I didn't even understand the definitions. Okay, and maybe that's the feeling you have. And then one day, this took this class with this professor. He already passed away, by the way. It's Francisco Caicedo, Pacho Caicedo, we call it. Uh-oh. Let me see. Is recording? Yeah. Okay. Oh, it's because I'm doing this. Is making a sign. So, so she showed us. He just like he really didn't prepare class. You know, he just come to class and he start writing definition, theorem. But then, that's something I learned from him. He just start proving the theorems without any preparation. He just always did this theorem, and then he start how I'm gonna prove it. And then he start going definition. This is what I need. This is and step by step by step. And then he said, okay, this is the proof. So at the end, he was not very organized. He didn't write the proof very carefully. Okay. And that's something that I would like to do here. So after doing the sketch, we write the proof carefully. But it really showed me how's the process. Okay. It's not, if you read the book, you're not even gonna understand the proof of the book if you don't try it before doing it yourself. You're gonna say, what's this? What? For example, some parts the book will say, let epsilon be 1. And you're like, why epsilon can be 1? Okay? So you really need to try to do your own proof and then go. So in my videos, I recommend you like stop the video when I'm gonna prove something. Stop the video, try to do something. You should try to do something. You will see that maybe you got some idea. You will understand the limitation of or why the problem is difficult. That's very useful. Okay, so you see, this class is a lot of training. So I talk, and now this is not moving up. Okay, now. So let's do the theorem. So let's say a proposition, Colette. It's called triangle inequality. And it's gonna be really important. We're gonna use this so many times in your life, in your future classes, that you'll be happy that we did this, okay? So that let A and B be any real numbers. Then the actual value of A plus B is less or equal the absolute value of A plus absolute value of B. And this is called the triangle inequality. Okay? So I'm gonna charge. Okay. So you want to stop the video? I'm gonna do two proofs of this. So my proof and the proof from the book. My proof is gonna be more complicated. So once I did my proof, and then I read the proof of the book. Oh, I think it was this book or another book. I don't remember. They said, yeah, this is easier because this one is coming from the definition, or from something we worked before. So stop the video, try to prove this to see what you get. Try 5 minutes and then come back. So now I assume you really try to prove this. And I'm gonna use this proposition we proved before. Sorry for the. I told you we will use this statement that we proved before, and is that the absolute value of x is less than a if and only if x is between minus a and a. So we're going to use that. So let me see if I can do the proof without sketch. Okay. So by definition, by proposition, I don't know what number, but if the actual value of x is less than epsilon, if and only if the proposition we know that actual value of x is less than epsilon if and only if x is between minus epsilon and epsilon, right? That makes sense because this is epsilon. Oh, sorry. This is x, this is x plus epsilon, and this is x minus epsilon. So if the actual values of x is less than epsilon, Oh no, but no, that's wrong. I'm here and wrong. Sorry. So yes, epsilon here, no? Epsilon and minus epsilon. And this is 0. So the distance, actual value is distance, no? X minus 0 is less than epsilon. So this is saying the distance of x to 0 is less than epsilon. Okay? So those are things, those are interpretations that for more that if you're not doing the exercise, those are things you miss. Okay, so that's why I try to do it myself, the proofs. So this is that, right? Now, what does it mean? What does it mean to us? So if you compare this with this, right? So what is your epsilon? How can you apply that statement here? So this guy, x, is this guy, right? So, and this is less or equal, right? So this is also less or equal. There's no problem with that. So this guy is less or equal than this guy. It means a plus b is between absolute value plus absolute value b, and this is bigger or equal than minus absolute value of a plus absolute value of b. Okay, that's what I mean. That's what we need to prove. What does it mean? So this, this guy is equivalent to prove this. Okay, so we need to prove that. That's what we want. So I'm gonna put it at the end. Okay. So that's what I want. So a plus b less or equal than absolute value of a plus absolute value of b, be equal minus absolute value of a plus absolute value of b. Okay. And this is equivalent to absolute value of a plus b less or equal to absolute value of a plus absolute value of b. Okay. So that's what I want. Okay, I want this, but this is the step before. Okay, using this proposition. Now, how can I get this? So I'm gonna address this part. I put it at the end. My message is not. Drop your vision. Let's see this. I'm not sure. No, doesn't erase very good. Okay. The technical issues as a regular class. Okay. Maybe need to understand this more. Okay. So let me just close it off. I'll erase it later. Okay. So I need to get this. Right? So how can I get this? As I said, this is not my proof. This is the proof of the book. So for me, it was not natural to figure this out. So That's probably that's why I didn't do it. Maybe for you it's natural. So can you think, how can you get that? So let me give you a clue. This is minus A, and then this is minus B, right? So the clue is this one, and it's like laid in this part. So the absolute value of A is less or equal than the absolute value of A, right? Is less or equal by itself. And by definition, by the definition, by this statement over here, this means A is very equal than minus absolute value of A and less or equal than absolute value of A. Okay. And same thing for B. Absolute B is less or equal to absolute value of B if and only if B is less or equal than minus absolute value of B less or equal to absolute value of B. Okay. Now, if you adding these two, we get a minus absolute value of A minus absolute value of B less or equal A plus B less or equal to absolute value of A plus absolute value of B. That is what we wanted, right? Because this is equivalent to this one. So this is the end of the proof. So I'm gonna have to cross it out because so let's go back to the proof. So by proposition of the book, we know that the absolute value of x less or equal than epsilon is true if and only if x is between minus epsilon and epsilon. We proved that in class. Okay. And now we said observing that the absolute value of A is less or equal to the absolute value of A, right? If and only if this is true by this proposition, right? By this proposition. And we apply the same proposition to absolute value of B. And then we add them together, you get that, and you get this. What did we do? It's charging now. So let me click something. So let me stop the recording, pause the recording for a second. Okay, so let's read the proof. So proposition, let A and B be any real numbers, then the absolute value of A plus B is less or equal to the absolute value of A plus absolute value of B. So by, let's say, previous proposition, we know that the absolute value of x less or equal than epsilon if and only if x is between minus epsilon and epsilon, right? So observing that the absolute value of A is less or equal than the absolute value of A, this is if and only if, assuming that by proposition, the absolute value of A is less or equal to the absolute value of A if and only if A is between minus the absolute value of A and the absolute value of A, and the same for absolute value of B, right? Adding these two terms, we get that minus actual value of A minus actual value of B is less or equal than A plus B less or equal than absolute value of A plus absolute value of B. And this is equivalent to this by the proposition, as we want. So this proof is very elegant, very nice, because it's just using basically this statement from this proposition we already used, right? I'm basically using it's basically using the definition of absolute value. Okay, so here's my proof. But I also using something, a proposition that is from homework. And I'm gonna sketch it, okay? And this video is getting too long. From homework, we know that if 0 is between A and B, then 0 is less than A squared, and A squared is less than B squared, and 0 is less than square root of A, and less than the square root of B. Okay? So, so here's how it goes. Well, I mean, I'm gonna do a sketch, and I haven't written it down, but I was like, I thought about a few minutes, and I write it down in a paper, very fast, just to show you like how we'll prove. So this is the sketch. So I want to prove A plus B less or equal than absolute value A plus absolute value B. Okay. So my intuition told me like sometimes you can do. Well, this is what is behind of this. I'm gonna do operations on this, and I'm gonna assume if and only if and only if and only if. And then when I get something true, I can just go back and rewrite the proof. Okay. So this is true. If this is true, but then sometimes you cannot just go back. So this way to do things. You have to be careful because maybe it's good in one direction, but not in the other direction. Okay. So I'm gonna take a square in both sides. If I take a square on both sides, what do I get? Say A plus B squared absolute value is the same as A plus B squared, right? Because absolute value of x equals square root of x squared. So if you take a square, this cancels. If this is true, then the inequality falls because this proposition is saying, right, that if both quantities are positive, then they're gonna the square holds. So if I do a square of this, that will be A squared plus 2AB plus B squared. Okay. And now I do my square here is A squared plus 2AB plus B squared. And this is less or equal than A squared plus 2AB plus B squared. But now notice what? The A squared is the same, the absolute value of A squared, right? That's what we're saying here. So basically x squared equals x squared. Because it's positive, right? And this same thing. So these two things are the same, so they cancel. Cancel, cancel, cancel. So I got 2AB is less or equal to 2 absolute value A times absolute value B. Now, is this true? This is true, right? So why? Because if A and B are positive, this is the same absolute value. If A is negative and B is positive, this is bigger. actually can eliminate just the two, right? If B is negative and A is positive, this is less than this is a quantity. So this is true. So I'm going to start my proof like that. So let me try to write like that. So let's try to prove the proof. And since AB is less or equal than absolute value of A times absolute value of B, right? And now look at what I'm going to do. By properties of inequalities, I can multiply times 2, right? 2AB, less or equal to 2AB. You see, I want to go backwards, okay? The properties of inequalities, this is true, but also I can add a squared on both sides, and I can add b squared and b squared on both sides, right? As I did over here, right? But noticing that this guy a squared plus 2ab plus b squared, noticing a squared equals a squared and b squared equals b squared, then this is, I just can replace this guy for what I want, the absolute value. Okay. And now, so I did this part, I'm going this here. Now I did this part. Now I do this part over here. So now, rewriting or simplifying, whether you're going to say a plus b squared is less or equal than absolute value a plus absolute value b squared, right? But this is, we already saw this is the same thing that a plus b squared. And now taking the square, now I use the other one, this proposition, you see? So now taking the square root on both sides, the inequality holds. So by homework, taking a square root on both sides, inequality holds. So you'll get a plus b less or equal and a plus b. Okay. So let me know if you don't like my proof or you find a mistake. But yeah, that's how I did it. Okay. And to be honest, I probably already saw it before, or somebody, I did it myself before. I'm sure I have done this before. So I don't know if that's my proof or I saw it from a teacher. I mean, I don't know. That's when I saw this. This is always, when I try to prove an equality, I always try to take squares and so on. So yeah, I hope you like it. Hope you like my proof better than the other one. To be fair, the other one still also use a proposition. Let me see if the book does it different. Not that. No, it's the proposition. It doesn't say it, but it's the same thing with the proposition. Anyway, but you don't need, he just put the proposition on the way, I think. Okay, good. So I think we can stop here. So thank you for watching, and I'll post my next video. It's gonna be sequenced. So we're gonna start talking about limits and all this stuff. Okay. Okay. Thank you guys. See.